3、2、1，点火！
点火！
At 12:41 on July 23, 2020, Beijing time, China launched the Tianwen-1 Mars probe at the Wenchang launch site in Hainan province. At 19:52 on February 10, 2021, after several midway corrections, Tianwen-1 finally entered the Mars orbit and was successfully captured by Martian gravity. At 7:18 on May 15, the Zhurong rover and the landing vehicle successfully landed on the Martian Utopia plane and sent back China's first photo of the surface of Mars and a selfie of the rover. At 10:40 on May 22, the rover left the lander and made close contact with the Martian ground to carry out missions of environmental science, geological science, and water resources exploration on Mars. So far, as the first Mars rover probe launched by China, Tianwen-1 has completed the three major technical steps of Mars exploration at one time. The three steps are orbiting, landing, and patrolling, which are entering Mars orbit, landing on the surface of Mars, and the rover walking and patrolling around. Why did China's space agency successfully break the so-called Mars curse with its very first Mars rover landing mission? How did the various aerospace technologies involved in the Zhurong landing process develop? Since the distance between the Earth and Mars is extremely far, and the surface environment of Mars is complicated, the journey of exploring Mars has been extremely difficult from the beginning. So far, the success rate of human probes to explore Mars is only 50%, and the success rate of Mars surface landing missions is only about 40%. Therefore, Mars exploration missions have always been called the Mars curse. Before China's Zhurong, only United States was able to safely send the rover to the surface of Mars, and the Mars rover missions of the former Soviet Union, Russia and Europe have not succeeded. To achieve the orbiting, landing and rover missions of Mars exploration, the country needs many key technologies, including but not limited to global deep space exploration network, heavy rocket launch and satellite orbit control capabilities, spacecraft atmospheric re-entry and autonomous soft landing technology and so on. The first is the Deep Space Exploration Network. Deep space measurement and control generally refers to tracking, telemetry, and remote control of satellites flying to the moon and beyond the moon by radio signals from the ground. If a country wants to achieve a global deep space exploration network, not only it needs to establish satellite monitoring stations within its own territory, but also it will inevitably need to seek international collaboration to achieve full airspace coverage. As one of the pioneers of Mars exploration, the United States built its own monitoring stations in its own territory, and also established deep space exploration facilities in Spain and Australia, and cooperated with the European Space Agency's Deep Space Tracking Network during the flight and landing of Perseverance rover. In contrast, China's Deep Space Exploration Network started late, but the starting point is very high. Since the 21st century, China has built or improved 7 aerospace exploration network sites in China, with a maximum antenna diameter of 70 meters. They are distributed throughout the country to ensure coverage of the widest possible airspace. Among them, the Kashgar Deep Space Station and Jiamusi Deep Space Station, which were put into use in Xinjiang by the Xi'an Satellite Measurement and Control Center at the end of 2012, have successfully completed the Chinese lunar rover and lunar sampling return plan, which is called Chang'e Lunar Exploration Project. In July 2015, when the U.S. New Horizons probe flew over Pluto for scientific observation, the Jiamusi Deep Space Measurement and Control Station successfully captured the probe's signal, and the longest tracking distance reached 4.76 billion kilometers. In September 2017, China's Deep Space Measurement and Control Network achieved tracking and measurement of the entire process of the crash of the U.S. Cassini probe to Saturn, which was a valuable experience for the subsequent implementation of more distant autonomous deep space exploration missions. In order to further meet the measurement and control requirements of the Tianwen-1 Mars rover, China's first deep space antenna array was completed in Kashgar, Xinjiang, on November 18, 2020, and various debugging and testing tasks were completed. The 3 newly built 35-meter diameter antennas and the original 35-meter antenna form a 4 by 35-meter deep space beam waveguide antenna array system, which achieves the data receiving capacity of an equivalent 66-meter diameter antenna and is suitable for various types of deep space missions with more powerful measurement and control support. In addition to stations within territory, in 2014, China and the Argentine government signed an agreement to build the first deep space measurement and control station in Las Lajas, Neuquén Province, Argentina. The Argentine Deep Space Station was successfully completed and officially put into use in 2017 for the development and use of outer space for Argentina and China. The geographical location of Yucaion is roughly symmetrical with China along the center of the Earth, which can provide support for the Tianwen-1 tracking in the western and southern hemispheres. In addition, just like Perseverance, the Tianwen-1 mission also cooperates with the ESA Deep Space Tracking Network. ESA monitoring stations in Spain, Australia and other places participate in signal relay and transmission. The development of China's deep space exploration network has laid a solid foundation for Tianwen-1 mission. Heavy rocket launch and satellite orbit control capabilities. For a country to achieve Mars rover exploration, advanced orbit control and attitude adjustment capabilities of heavy rockets and satellites are indispensable. As the world's first Mars probe to complete orbiting, landing, and patrolling in one single mission, Tianwen-1 is a giant with a total weight of 5 tons, about 4.9 times as heavy as American Perseverance rover in terms of total launch payload weight. The rocket thrust required to send such a 2-truck weight probe to Mars orbit is extraordinary. Among the world's active rockets, only 3 have an Earth-Mars transfer capacity of more than 5 tons. They are NASA's Delta IV Heavy rocket, SpaceX's Heavy Falcon rocket, and China Aerospace Science and Technology Corporation's Long March 5 rocket. The Long March 5 is China's first large-scale liquid oxygen hydrogen and liquid oxygen kerosene carrier rocket series that adopts the latest technology from the overall to the subsystems. It is the Space Transportation System project with the largest scale and technology span developed in China, and the proportion of new technologies is up to above 95% compared with previous Long March rocket series. At present in China, it is the rocket with the largest takeoff mass, the largest core stage diameter, and the strongest carrying capacity in active service, with a low Earth orbit payload of 25 tons, ranking 3rd in the world. Its Earth-Mars transfer capability of 6 tons meets the mission requirements of Tianwen-1. On July 23, 2020, the Long March 5 rocket equipped with the Tianwen-1 probe was launched at the Wenchang launch site in Hainan. This is the 4th successful launch of the Long March 5 series rockets and the 219th launch of the Long March carrier rocket family. In recent years, China's rocket launch activities with large numbers, high payload and high success rate have laid a solid foundation for Mars rover mission. From the data of rocket launching, China's annual number of rocket launches has remained at around 40 in the past 2 years, which is about the same as that of the United States. Every year, many large-scale remote sensing satellites, beta navigation satellites, weather satellites, agricultural census satellites and other space infrastructure construction are being conducted. It can be said that after decades of technology development in China's aerospace industry, carrier rocket technology and satellite orbit control are already well established. Among CNSA's missions, the Chang'e Lunar Exploration Project is a pioneering project for deep space exploration paving the way for Mars exploration. From the launch of Chang'e 1 in 2007 to the lunar soil return mission of Chang'e 5 in 2020, during the 13 years, the deep space orbit control and maneuverability of China's spacecrafts have been well tested. By applying the attitude and orbit control experience gained in the Chang'e project to the Mars rover mission, it is conceivable that Mars probe orbit control is not a key challenge for China's spaceflight. In the several orbit adjustments of Tianwen-1 in 2020 and 2021, we can see that every orbit maneuver of the probe is accurate. Due to the high accuracy of orbiting, the orbit midway correction originally planned to be carried out on February 12, 2021 was even cancelled. The orbit was adjusted directly on February 15, and a 90-degree right-angle turn was carried out at the apogee, from a horizontal orbit to a vertical orbit around Mars, and the probe entered the Martian polar orbit to achieve the best orbiting coverage of Mars' surface. In fact, as a relatively simple part of the entire probe's itinerary, many countries other than the United States and Russia also tried to launch orbiters to Mars after the Cold War, including several ESA probes, India's Mangalyaan and the UAE's Hope probe, which have been successful in cooperation with the International Deep Space Exploration Network, and have also made important contributions to humans' exploration of Mars. Compared with orbiting Mars, the most challenging aspect of the Mars mission is the rover's soft landing. The landing process of the Mars rover is called 9 minutes of terror, and in some circumstances, it is also called 7 minutes of terror. This process is generally called EDL, which is the abbreviation for entry, descending and landing. The whole process needs to rely on the autonomous control of the lander. In human history, the success rate of Mars soft landing missions is less than half. For CNSA, it is the first attempt to softly land a rover lander stack weighing more than 1 ton on the surface of Mars, and it is truly a new challenge. And because of the well-known difficulties, the successful landing of Tianwen-1 to some extent shocked some of the public who didn't pay much attention to China's aerospace industry. However, if you really learned the development path of China's deep space exploration missions, you will not be particularly surprised at the complete success of Tianwen-1. After all, opportunities are always reserved for those who are prepared, and the Mars soft landing mission is no exception. Due to the unique atmosphere and gravitational environment of Mars, there are three key technical actions in the soft landing process. 1. Overheat protection and attitude control during deceleration after the spacecraft enters the atmosphere. 2. Parachute deployment at supersonic speed. 3. The autonomous obstacle avoidance and soft landing technology of the lander. Similar to the Earth, Mars also has an atmosphere surrounding the surface, so the spacecraft must undergo violent friction with the Martian atmosphere before landing, and the surface temperature of the spacecraft can even be higher than 1000 degrees Celsius. This requires the landing equipment to have excellent heat protection measures and aerodynamic shapes, so that it can keep the detector's electronics intact during the friction with the Martian atmosphere and avoid overturning. Atmospheric re-entry is not new to China's space programs. Looking back on the historical development trajectory of China's spacecraft re-entry, since 1999, the Shenzhou series of spaceships experienced severe friction with the atmosphere every time when capsules re-enter the Earth's atmosphere. Since 2003, 11 Chinese astronauts have entered space and returned safely. With the opening of China's Tiangong space station, 12 Chinese astronauts will enter space and return to Earth in the next 2 years. The Chang'e F5T1 re-entry and return flight tester launched in 2014, and the Chang'e F5 return capsule, which retrieved the lunar soil and returned to the Earth in 2020, tested the safety and reliability of the spacecraft's re-entry into the atmosphere at the second cosmic speed. It can be said that key technologies such as aerodynamic shape design, attitude control, and thermal protection materials for the spacecraft's re-entry into the atmosphere were already well established and tested before Zhurong landed on Mars. During its landing process, the back heat shield and the bottom heat shield played the role of heat insulation. The attitude control nozzles and balance wings outside the heat shield prevent the spacecraft from rotating axially and ensure stable attitude. In order to further enhance the heat insulation reliability of Tianwen-1's entry into the Martian atmosphere, the 306 Institute of the China Aerospace Science and Industry Corporation has designed a new type of thermal insulation material for the probe, the nano aerogel. It will be used to deal with both extremely hot and extremely cold environments. At the same time, the ultralight characteristics of the nano aerogel also greatly reduces the burden on the rover, allowing it to run faster and farther. In addition, in order to withstand the risk of uncertainty brought by the Martian atmosphere, China has adopted a unique ballistic lift-type atmosphere entry scheme based on the so-called balance wings for the first time of humans' Mars exploration. This solution has a long deceleration time and small overload during the entry process. It can also improve the landing accuracy of the probe by controlling the lift direction. It is also an ideal entry method for future Mars sampling and return and crewed Mars landing missions. Previously, the Chang'e F5 return capsule also successfully landed on the Earth using the same technology. Compared with the atmosphere of the Earth, an important difference of the atmosphere of Mars is that its density is only 1% of the atmosphere of the Earth. In order to reduce the speed of the probe to a safe range of less than 100 meters per second before releasing the lander, in addition to the friction between the Martian atmosphere and the insulating shield, the probe also needs the assistance of a parachute. On Earth, due to the high atmospheric density, the speed of the spacecraft can generally fall below the speed of sound before the parachute is deployed. However, the thin atmosphere of Mars makes the probe have to deploy the parachute during the supersonic flight period to decelerate in time. The supersonic parachute system of the spacecraft posed a huge challenge. It is also a key factor leading to the repeated delays of the Mars exploration programs of Europe and Russia. As early as 2016, the 508 Institute of China Aerospace Science and Technology Corporation completed the wind tunnel test of the supersonic parachute. In 2018, the new Tianyin series of sounding rockets developed by China Aerospace Science and Technology Corporation were successfully launched at the Korla launch site in Xinjiang and successfully carried out the supersonic parachute technology test for the landing of the Mars probe, which laid another technical foundation for landing on Mars 3 years later. After the supersonic parachute reduced the probe speed from Mach 2 to 95 meters per second, the responsibility of the last step of the Mars soft landing falls onto the lander. Different from the sky crane of the Perseverance Mars rover, Tianwen-1 uses a reverse thrust hovering landing scheme. The landing platform carrying the Mars rover will activate the reverse thrust system when it is close to the ground, allowing the platform to slowly descend. At 100 meters from the surface of Mars, it enters the hovering phase. With the help of optical imaging sensors and other measuring equipment, after completing the precise obstacle avoidance and slow descent, the probe arrives on the surface of Mars under the protection of the buffer mechanism. The key component in this process is the 7,500 Newton variable thrust engine. Through the throttle control of a single engine, the lander can achieve a series of complex actions such as deceleration, hovering, obstacle avoidance, and slow landing. China's 7,500 Newton variable thrust engine has been developed since 2008. It has successively completed engine verification, design, appraisal tests, process research, and hot fire test. It was used on Chang'e 3 for the first time in 2013. It helped Chang'e 3 successfully land on the Moon in reverse thrust hovering mode, making China the third country after the former Soviet Union and the United States to successfully achieve a soft landing on the Moon. Relying on this engine, the Chang'e 4 in 2018 made China the first country to softly land on the backside of the Moon. In 2020, still relying on the stable performance of the 7,500 Newton variable thrust engine, the Chang'e 5 landing and ascending complex successfully landed on the lunar surface and returned to the Earth with lunar soil. In addition to variable thrust engines, as the distance between Mars and the Earth is hundreds of millions of kilometers, the fully automatic landing procedures and autonomous obstacle avoidance capabilities required for the probe's landing have also been verified in the Chang'e 3 to Chang'e 5 missions. It is easy to see that the technological experiences in the Chang'e exploration missions have added confidence to the success of the three major goals of Tianwen-1 mission. From crewed spaceflight to the exploration of the Moon by Chang'e, and now the Zhurong Mars rover mission, the CNSA scientists are advancing the technology step by step. Especially under the condition of tight budget in the early stage, it was still making steady progress, breaking through key technologies year by year and carrying out tremendous amounts of technical tests in accordance with the existing project planning and roadmap. As early as 2004, China's lunar exploration mission set the goal of completing the 3 steps of Moon orbiting, landing and sample returning by 2020. With the ending of Chang'e 5 mission in December 2020, it was successfully completed. Also, as early as 2000, China's space station missions formulated the plan of launching crewed spacecraft, astronaut spacewalk, launching the space laboratory, and building the space station by 2022. Without exception, these plans are progressive, steady, and timely. As for Tianwen-1, which has inherited the tradition of China's space programs, even though the project was officially established in 2016, the technologies directly or indirectly used in it have been accumulated in CNSA space explorations for more than 10 years. Based on these technologies, China's future space plans such as the Super Heavy Long March 9 rocket, lunar space station, sampling Mars soil and returning to Earth, exploring the solar system edge, are all attracting space fans' attention. After all, for a certain period of time after the Cold War, the pace of mankind's exploration of space has slowed down slightly, and the rapid development of China's space projects is also injecting strong impetus into the world's space exploration. Perhaps the new wave of space exploration that space enthusiasts are looking forward to is just beginning. Thank you for your watching and likes. In the future, there will be a richer introduction of China's space program history in this channel. How did CNSA start and develop step by step to today's scale and technological level? Please subscribe and tab the bell if you are interested in CNSA's programs. Stay tuned and see you next time.